Very good morning to all of you. We are going to continue the Laplace transform with the first property, linearity property. After we have shown that 7 basic formula of Laplace transform in the previous video, where the Laplace transform for A, you have A over S. Laplace transform for t power n, you have n factorial over s to the power of n plus 1. Laplace transform for exponent at, you have 1 over s minus a. Laplace transform for sin at, a over s squared plus a squared. Laplace transform for cos at, s over s squared plus a squared. Laplace transform for hyperbolic sinh at is a over s squared minus a squared. Laplace transform for cos at, you have s over s squared minus a squared. Now we are going to learn several properties for Laplace transform. The first one is the linearity property. Here, if f1t and f2t have Laplace transform, alpha and beta are scalar, so the Laplace transform for alpha, where is a constant value, for example, make alpha 3, Laplace transform for alpha f1t plus minus beta f2t, using linearity properties means, okay, if alpha beta are some constant value, you may factor outside to the Laplace symbol, and if you have the plus minus, you can break the symbol of Laplace into true. So mean you have Laplace transform for alpha f1t plus minus Laplace transform for beta f2t. Beta is a constant, you can factor outside of the symbol of Laplace transform. Okay, for example, find the Laplace transform for 5t cubed plus 60. Hence, you can break it become Laplace transform for 5t cubed. 5 is constant, factor out. So plus break it become Laplace transform for 6t. 6 constant, you factor out. Okay, and Laplace transform for t cubed. T cubed using back, okay, the second formula, t cubed, so 3 factorial over s to the power of 4. So t cubed 3 factorial, which is 6 divided by s to the power of 4. Laplace transform for t will be t power 1. So you have 6 times 1 factorial divided by s squared. Simplify it, you have when you factor 6 over s squared. So the first term, you have still left 5 over s squared. This is plus 1. So this is the linearity property. Okay, the second property, we have the first shift property, which says that if Laplace transform for ft, you have fs, and a is a scalar, then Laplace transform for exponent at ft will be equal to fs minus a. Okay, notice that you have the product form of ft multiplied with Laplace transform for at. Okay, using first shift property, the result is fs minus a. Okay, don't try to break your Laplace symbol if you have a product form. Okay, this one, don't break it as Laplace transform for exponent at multiply Laplace transform for your ft. Okay. Mean Laplace transform for exponent at ft. You know the Laplace transform for exponent at is actually 1 over s minus a. Okay, but you cannot, if you have a product form, you cannot break the Laplace transform like what you break using the, if you have plus minus, you can break it, but multiply or divide, okay, you cannot break the symbol of Laplace transform. This is wrong. Please take notes that. So if you have the product form of ft multiplied with exponent at, you have to use first shift property. When you find the Laplace transform for ft first, which is fs, and then multiply with exponent at, s here you replace by s minus a. Okay, to prove this formula or this property, you can use the definition of Laplace transform. Okay. Now your ft is actually definition of Laplace transform. Call back your definition of Laplace transform. Laplace transform for ft will be integrate exponent negative st ft dt from 0 to infinity, where the ft now is exponent at ft. Exponent at ft. Yeah. Exponent at ft here. Okay. Later on, you combine the exponential term using the index rule, become exponent negative bracket, so negative st, negative negative, so plus at. Okay, and later on, replace the s minus a by p. Okay, hey, look that. Okay, using definition of Laplace transform. Okay, call back here. Laplace transform for exponent negative st ft. The result is fs. Result is fs. So if integrate exponent negative pt ft, then the result will in terms of parameter p, where the p is actually fs minus a. So this is what we call the first shift property. Laplace transform for exponent at ft will be equal to fs minus a. Okay, for example, use first shifting property to get the Laplace transform for exponent at. Even though you have we have derived the formula for Laplace transform for exponent at is actually 1 over s minus a using the definition of Laplace transform. Here we purposely want to show the first shift property, to get the exponent at, where the exponent at you can rewrite as exponent at multiply 1. If you tally it, means your ft is actually 1. So you have to find the fs. Laplace transform for 1, you have 1 over s. So if you have the Laplace transform for exponent at multiply ft, the result is fs minus a. So this is fs. So now s replaced by s minus a. That's why the Laplace transform for exponent at using first shift property, again you can get back the same formula, which is 1 over s minus a, as what we have shown in the previous lecture video. Laplace transform for exponent at is 1 over s minus a. This is shown using the definition of Laplace transform. Okay, second one, we want to find the Laplace transform for t exponent at. So you compare with the first shift property. Laplace transform for exponent at ft is fs minus a. Hence, before you can find fs minus a, you have to find fs. To find fs, you have to identify your ft. Okay, the ft here is t. So this is ft. You have to form exponent at ft, where the ft is t. So the fs, Laplace transform for t is 1 over s squared. 1 over s squared. Remember, t power 1. So 1 factorial divided by s squared. So Laplace transform for t is 1 over s squared. So t multiplied by exponent at using first shift property. Where you replace the fs here, s replaced by the bracket s minus a squared. Okay, the third one, Laplace transform for exponent alpha t sin beta t. Okay, this is the ft. Ft is sin beta t. So we have the form exponent at, where the a, in this case, the a is equal to alpha, exponent alpha t ft. Ft is sin beta t. So Laplace transform for ft or sin beta t is beta over s squared plus beta squared. Hence, Laplace transform for exponent alpha t sin beta t from the fs, s here replaced by, so make sure bracket, s minus alpha squared. Okay, the third property is multiplying by t to the power n property. Again, if Laplace transform for ft is fs, then for the positive integer n values, 1, 2, 3, and so on, Laplace transform for t to the power n ft will be negative 1 to the power n dn dsn. Okay. Or Laplace transform dn dsn Laplace transform for ft, which is fs. In the Laplace transform for tn ft is actually negative 1 to the power n dn dsn fs. Fs is actually Laplace transform for the ft. Okay. For example, if you have Laplace transform for t power 1 ft, then it's negative, n is 1. So negative 1 power 1 is, so you have negative d ds fs. Okay. Fs is you have to find the Laplace transform for your ft. Okay, for example, okay, 1, find the Laplace transform for t exponent at. Okay, this one we have shown just now using the first shift property, right? T exponent at. The result is 1 over s minus a squared. Now we are going to show it using multiplying by tn property. Hence, okay, your t power 1, so it will be negative 1 power 1 d1 ds1, so means negative dds. The fs is actually Laplace transform for your exponent at, which is 1 over s minus a. Okay, when we differentiate respect to s, so it will be negative d ds 1 over s minus a will become, okay, s minus a power negative 1. So for differentiations, we multiply the index here. So negative times negative 1. Okay, negative times negative 1 become positive 1. And then for differentiations, so the index will be decreased by 1. So become minus 2. Power minus 2, which is actually 1 over s minus a squared. And then your dds here 1s, which is 1. That's why the result is 1 over s minus a squared, which is tally back with what you obtain using the first shift property. Okay, if second question, Laplace transform for t squared. T squared can be rewritten as t times tat. Okay, because tat is result from a here. So mean it's only t power 1, mean this one you assume the whole thing here as your ft. So Laplace transform for t times ft, so it's negative dds fs, where the fs you obtain from result a here, 1 over s minus a squared. Okay, and then we make it become negative d ds s minus a power negative 2. So for differentiation, the power become multiplied in front here, so negative times negative 2. So you have positive 2, then s minus a power negative 2 minus 1 more. So power negative 3 is actually 1 over s minus a power 3. And your DDS, 1s here you have 1. That's why the result is 2 over s minus a power 3. Okay, then let's say we look at the last one, D. Question C, I think you can try it yourself. Okay, Laplace transform for t squared sin t. Okay, it's actually do it from the question C first. Laplace transform for t sin t. I mean, this is actually you differentiate 2 times. So, but the first time the result, okay, here Laplace transform for t sin t is negative dds. Laplace transform for sin t, which is 1 over s squared plus 1. And then okay, differentiate this one. We have negative against negative dds s squared plus 1 minus 1. So minus and negative. So negative, actually you have positive. And then okay, s squared plus 1 minus 1 minus 2. Minus 2 is 1 over s squared plus 1 squared. And you need to differentiate s squared. You have 2s. So that's why the result is 2s over s squared plus 1 squared. Positive because negative multiply negative 1 positive. The 2s is come from your dds s squared plus 1. You have 2s here. Okay. So 1 over s squared plus 1 squared is because, okay, for differentiation, the index will be decreased by 1, become power negative 2. It's actually 1 over s squared plus 1 power 2. Okay, to differentiate it, t squared is actually Laplace transform for t multiply t sin t is here. The result is here, 2. So Laplace transform for t power 1 is negative dds. Okay, this is the result from t sin t, which is 2s over s squared plus 1 squared. And here you need to use the quotient rules to differentiate it, because your numerator is not the constant value, it's not a constant value, but it's a function of s. So it will be easier you use a quotient rule to differentiate it, where negative dds 2s over s squared plus 1. So the negative is from here. You should have v du. Mean, okay, remember you ds u over v. You have the v u prime minus u v prime over v squared. So this is v squared, so power 4. So v is s squared plus 1 squared. U prime, you have 2. The minus is from here. So minus u 2s. V prime, 2 s squared plus 1 power 1. And then dds s squared plus 1, you have 2s. And then what we do is actually we try to cancel out. Here you have s squared plus 1 power 1. Power 1. So this power 1 cancel with here. This is 3. This is cancel out 1. So you left 1. So 2 times s squared plus 1 power 1. So minus 2s times 2 times 2s. So total is 8 s squared. This is 8s squared. So minus something like 6s squared minus 2. This is minus 2s squared. Minus 2s squared. This is minus 6s squared. So let's do it first. We have like here minus outside. So this is a 2s squared minus 2 times 2 times 2 minus 8s squared divide this one, the s squared plus 1 power 3. The minus belong to outside of this here. So this is 2s squared. Sorry, here you have a plus 2. You have 2s squared minus 8s squared will become minus 6s squared, outside negative, so 6s squared. So negative and 2, so minus 2 over s squared plus 1 cubed. Okay, if this can cube for your attentions.